Hello and welcome to my lesson. My name is Mr. Johnson and this is one of my 20-minute lessons. I'm going to be talking to you today about atomic models, which is one of the radioactivity series of the physics GCSE. And yeah, here we go. I'm going to share my screen with you and then you'll be able to see what I'm talking about. Okay, so atomic models then. Oops. What I'm hoping you'll be able to do by the end of this is understand how ideas about the structure of the atom have changed over time and why. And this involves being able to describe the structure of an atom in terms of nucleus and electrons, describe how and explain why the atomic model has changed, and understand and explain where most of the mass of an atom is found and the supporting evidence for all of this. So, first off, if I asked you to draw a diagram of a lithium atom, if you're watching this, you want to pause the video and just take a stab at it. Lithium has the symbol Li73. What you should be doing at this point is what you would have been taught probably in your chemistry classes as much as your physics. So you'd be drawing a nucleus that contains 3 protons, hence the atomic number 3. 4 neutrons, because 3 plus the 4 gives an atomic mass of 7, and the nucleus contains all the mass. And that would be located in the center of the atom, or the nucleus, with 2 electron shells, because lithium is in period 2 of the periodic table. 2 electrons in the first shell, and 1 electron in its outer shell, because it has the same number of electrons as it does protons, as it's an atom, so it's uncharged. And it's in group 1 of the periodic table, meaning that one of its electrons is in the last shell. How did we get to this? Where did this come from? Most people are taught this, just accept it. There's no idea as to why that's happened. And that's the point of this lesson. Where did this model come from? Where do the subatomic particles fit into the atom? What's between them? How are they held together? Most of the time, when you ask a pupil this question, they get a bit stuck. They do know, they just don't know how to put it in. But in theory, what you should be saying is that the protons and neutrons are together in the center of the atom. This is the nucleus. Electrons whiz around the nucleus in shells. Between them, there's only empty space. There's nothing there between the electrons in the shells and the nucleus except for space. They're held together by forces of attraction between the oppositely charged particles, the proton and electron, and by the presence of the neutrons, which is preventing the proton-proton repulsion and keeping the nucleus together. This is our modern example. That's our first point. Describe the structure of an atom in terms of the nucleus and electrons. Our second point then, describe how and explain why the atomic model has changed. We've learned in the past, year 6, year 7, year 8, that all matter, whether solid, liquid or gas, is made out of things that's too small to see by our naked eye. We call these things particles. We normally represent particles as spheres. As an example in the picture there, we've got an oxygen atom, red sphere, and we've got carbon dioxide modelled using a black sphere for the carbon and 2 red spheres for the oxygen. We can also represent them much like we do in chemistry when we're talking about bonding. In this case, we've got covalent bonding shown between carbon and oxygen for carbon dioxide. And here we draw them again as circles, as spheres. This is another representation of that. We can explain some of the properties of different elements by thinking about the particles or the atoms that they contain. In a chemical reaction, atoms in substances get broken up and joined together in a new way. So the reactant atoms are broken up and then they are rearranged and rejoined to give the products. The products cannot contain an atom that wasn't present in the reactants, nor can the reactants produce a product that contains different atoms to what they started with. It's a bit like breaking up a Lego model of a house and using that to build a car. You can't build the car with, say, a purple brick if there wasn't purple bricks in the starting kit that you got from breaking up the house. So, in 1897, a scientist called J.J. Thomson found that atoms contained even smaller particles inside of them. And this was the first discovery of the electrons. Electrons were found to have a negative charge and nearly no mass. Now this left Thomson a bit perplexed because we know that atoms have mass. So what was going on? Well, in 1900s, Thomson supported using a new model of what the atom was really like to explain this new evidence. This new model was called the plum pudding model. It described the atom as a pudding made of positively charged material with negatively charged electrons scattered throughout it. And the idea is, think of a sponge with currents in it, the sponge representing a distribution of positive charge and the currents representing electrons just scattered through it, and you'll get the idea. Pretty much this idea here. So, just taking a segue sideways for a moment, how does particle theory explain why solids have fixed shape? And positive and negative charges cancel each other out, so how does the plum pudding model explain atoms have no overall charge? Well, first off, particle theory explains why solids have a fixed shape. You have this idea from year 7, and it's because the particles are held together in fixed arrangements. That idea of all those spheres next to each other with very little space between them, meaning that they're in irregular fixed arrangements and they can't move, that gives them a fixed shape. Secondly, the negative charges and the electrons balance or cancel out the positive charge in the pudding part of the atom. And that is how the plum pudding model explained atoms have no overall charge. It was balanced, pretty much similar to the idea we have today, only the structure of the modern atom is different. That's describe how and explain why the atomic model has changed. So between 1909 and 1913, a team of scientists led by Ernest Rutherford tried to improve the model of the atom at the University of Manchester. Now they fired positively charged particles called alpha particles at gold foil. This was their experiment. It was designed as such. The middle of the room was a thin gold piece of foil. This was contained inside a vessel that had all the air removed. This was to prevent the alpha particles from the source being interrupted by any other particle in the way. The idea was to remove anything but the gold foil so that the only thing the alpha particles could interact with was the gold foil, and that was it. A radioactive source was placed in this vacuum vessel, and that radioactive source directed alpha particles directly at the gold foil. Now, what we saw whilst using a detector to monitor the other side of the gold foil from the source was that most of the alpha particles went straight through it. Some alpha particles were deflected, and some of them were scattered through really large angles, almost 90 degrees in fact. The detector could be moved around to count for this, and they gave out flashes of light when a charged particle hit it. And this then was the modern experimental evidence for the atom that we know and draw today. So it was thought that the alpha particles could pass straight through the gold foil or puncture it. It's what should have happened if the plum pudding model was correct. The alpha particles would have passed through this evenly distributed positive charge sphere, and they would have slowed down a bit, but they would have passed straight through. Instead, Rutherford and his team found out 3 very surprising things. First one, most of the alpha particles did pass through the foil, which, all right, not so surprising considering that was what they were expecting. But a small number of alpha particles were deflected through an angle as they passed through the foil. And that was like, what's going on here? But thirdly, a very small number of the particles bounced back off the foil, were deflected at really, really large angles. And this could not be explained by the plum pudding model. That was a say what moment. Here we go, some diagrams of what's actually happening and how it relates to the structure of the atom today. Most of the particles pass straight through because now we know that most of that is the empty space between the atom's electron shells and its nucleus. Some particles are deflected by a small amount. This is because the alpha particle being positively charged came close to the region of positive charge in the nucleus, and that caused repulsion forces which deflected its path away from where it would have gone if it had passed straight through. Some of those particles were bouncing back, and that was because they were hitting or directly making contact with this dense, heavy nucleus. Now, we talk about it being dense and heavy. In the sense of it meeting an alpha particle, it was. Gold has a really dense nucleus compared to an alpha particle, which essentially only has a mass of 4. So it bounced back off like someone kicking a football at a wall. So what did this mean then? Why did the particles pass through some of the time? Why did some particles deflect? Why did a small number of particles bounce back? Well, we've touched on this in the last slide. But Rutherford suggested that this meant the following. Most passed through because there was a lot of space inside the atom between the protons and the electrons. Some were deflected because they passed a region of concentrated positive charge, and because like charges repel, they were repelled away from it. This was most likely a lot of protons in one place inside the atom. Finally, the very few that were bounced back indicated that the positive charge was concentrated in a really small space, which he called the nucleus of the atom. And he said that's why so few had hit it and bounced back, because it was a very small space. This then led to the adaptation to the plum pudding model, rejection of it, and the model that we now know, with a small central nucleus, which is dense, containing most of the mass of the atom, and in a region around it, electrons orbiting. What it didn't actually give rise to, which came later on, was the idea of electrons in shells. Rutherford's model literally stated that the electrons were present in a cloud around the atom's nucleus, and that there was space between the nucleus and the electrons. Today, we know that the radius of a nucleus is about 1 × 10⁻15 meters, which, if we're to write out as a number, is that one there, 0.0000000000000000001 meter. The radius of an atom is about 100,000 times larger than that, 0.00000000001 meter. So the atom itself is about 100,000 times bigger than the nucleus inside it. And as an example of this, if the atom had the same diameter as the entire dome of the O2 Arena in London, its nucleus would be the size of the dot on the screen. So how does this work then? Well, this is a 6-mark question that came up on my exam board's papers a couple of years ago, and it's a good way of looking at the information that's been given here. It's talking about Rutherford's scattering experiment. The student fire a beam of alpha particles, a thin piece of gold foil. Figure 10 shows the arrangement of the experiment. It's a simplified version of the diagram that we've seen, but we've got the vacuum chamber with the ringer detectors around it, as represented by the circle. Inside, the alpha source emitting a beam of alpha particles. The gold foil is the thin line at cross section to that. And then P, Q, and R, 3 points where particles are being detected. Some particles were found at all parts of the ring detectors. We've been given a table. Explain what the information in figure 10 and figure 11 shows about the structure of an atom. So for this, it needed information from the diagram, the table, but to get 6 marks, you had to relate it to your knowledge of the structure of the atom. You couldn't just say, oh, the diagram shows this and the table shows that, and expect to score 6. You had to link it to the knowledge of it, and that's where this lesson ties all that together. So first off, from the diagram, most of the alpha particles went straight through to P. That was the information from the table and the diagram. And the linked knowledge is that this is because the atom is mostly empty space. So it's passing in that region between the electrons and the nucleus. Some are deflected through small angles to Q. Notice I'm saying which ones are being deflected and to which point in the diagram. This is because the positive alpha particle is being repelled by the densely positive nucleus. Fewer have deflections greater than 90 degrees to R. This also tells us that the nucleus is very, very small in relation to the size of the atom, or they're even reflected or bounce back off the foil to R, telling us that there's a positive charge concentrated into a very small space, and that the nucleus has a large mass or density. This would have been 6 marks just for 3 statements in red, followed by 3 linked statements in green, because you've linked the fact that most, some, and few from the table go to P, Q, and R from the diagram, and then in green, you've linked that to your knowledge of the modern atomic structure. And that's the end of this lesson for now. So I'd like to say, once again, thank you for joining me, and I hope you enjoyed it. See you again next time.